Welcome everyone. So it's my pleasure to welcome Arash Mehrjou. We'll be talking about neural Lyapunov redesign. Yeah, thank you very much.
Yeah, thank you very much, Boumediene, for the introduction, and thanks a lot for organizing this seminar, also inviting me to give this talk today. So as can be seen on the screen, this talk is the title of the talk is Neural Lyapunov Redesign, which is actually an effort to combine ideas from machine learning and control theory, especially nonlinear control theory. So this is a collaboration with Mohammad Khabamzadeh from Google Research and Bernhard Scholkow from Max Planck Institute for Intelligent Systems, where I'm also affiliated with. Okay, so I'll start with some preliminaries and some notations. Nonlinear systems can be represented as this ODE, like x dot equals f of x, where f shows the vector field. It's basically so the vector field is a function from Rn to Rn, which is actually the dynamics, the model of the dynamics of the system. X0 is the starting state of the trajectory, or the initial state. And we can say, from machine learning perspective, we can say that every trajectory is basically an experiment. So we can say that actually every experiment provides some information about the desired, let's say, the desired object that we want to estimate. Especially if we have the limited experimental budgets, then we are more interested in designing these experiments in a more clever way. Also, the initial points sometimes cannot be chosen freely when you want to do experiments, then you have to choose them in a way that also meets the limitations of the system. All right, so the equilibrium of the system is where the vector field vanish. So which means that f of x bar equals 0. And also we define the flow functions phi t and x0 as the integration of the vector field over time. So the region of attraction, which is a essential and important component in this project, and also which also plays an important role in what I will actually present as the concluding remarks, which will be kind of beyond the scope of these projects, but would be some sort of a overall idea that I will present at the end. So the region of attraction is the set defined as all the states or initial states around the equilibrium that will eventually converge to the equilibrium. So the trajectories are usually sampled at discrete time in practice. So this is a practical considerations, and then just for convenience, for every equilibrium, we show the region of attraction corresponding to an equilibrium x bar by r subscript x bar. So we know that region of attraction is hard to compute for a given vector field, unless the vector field is very simple, or maybe it meets some certain conditions, but it's not easy to compute for an arbitrary vector field. But there is actually there is some lemma that shows that we can use the Lyapunov function as a way to approximate the region of attraction. So the Lyapunov function has some theorems that actually supports this claim that we can use the Lyapunov function and some sub-level sets of the Lyapunov function as an inner approximation of the region of attraction. So as you see here, the Lyapunov function satisfies some conditions. And the more important condition is that the Lie derivative of the Lyapunov function along the trajectories of the system must be negative. So it's called the negativity condition. And then, given this condition and also the positivity of the Lyapunov function, we can see that there exist some sub-level sets of the Lyapunov function which are contained within the region of attraction. And then this means that if you find a good Lyapunov function, then this region of attraction or this sub-level set can be a good approximation of the region of attraction. Okay, so now the one question is, how can we actually estimate the region of attraction? So as stated, the region of attraction cannot be estimated for general nonlinear systems. So but we are interested in estimating it anyways. And so there are methods, especially the method the Lyapunov function, and then uses the samples taken from the samples taken from around the boundary of the Lyapunov, around the boundary of the estimated region of attraction to solve a classification problem. So basically, the phrase learning a Lyapunov function as a classification problem for which we have well-developed methods in machine learning. So the important aspect of this method is that it's iterative, and it's an evolving algorithm. Basically, it starts with a very conservative approximation of the region of attraction, and then it improves over time and over iterations. And by improve, I mean the Lyapunov function gets better in a way that the sub-level sets gets closer to the region of attraction of the system. And this continues until given the enough expressiveness of the neural network that estimate the Lyapunov function, it can eventually converge to the state or to the Lyapunov function whose level set, or there exists one level set for this Lyapunov function that is a very good approximation of the region of attraction. So as you see, for example, in the top right, there is so at each stage, it samples from around the region of attraction, the current estimate of region of attraction. So assume that this blue region shows the current estimate of the region of attraction, which is some level set of the Lyapunov function. And then by multiplying the value or the level value, we can achieve a larger level set. And this means that we can sample from this larger level sets. Also, we can multiply that level value with the larger numbers. And this actually makes that level set a little larger. And at some point, it also goes to the unstable regions in the data space, which are next to the boundary of the region of attraction. And then this means that for every, so around this region of attraction, we have both negative and positive samples. So the negative samples are the initial states that go beyond, which are unstable, meaning that their trajectory do not converge to the stability region, but within the region of attraction, or let's say the samples taken from within the region of attraction goes back to the stability regions. And we know that these are invariant sets, meaning that if they enter these regions, the trajectories will not leave it. And then with this condition, we can assess this condition by rolling out trajectories and then assign labels to the samples, to the initial states, and then solve the classification problem. So the classification problem gives us the boundary for region of attraction. And then when we have a boundary, then we can again do sampling and solve another classification problem. And this goes until we meet some stopping criteria. So in an earlier work, we combined this algorithm, this iterative Lyapunov function estimation algorithm, with the ODE learning algorithm. So the idea was to use the estimation of the Lyapunov function for two purposes. One is to do experiment design, meaning that how can we collect samples which are more informative about the ODE within the region of attraction, and also how can we regularize the learned ODE by this sample, by the Lyapunov function. So I won't go into detail of this work, but so this is just one slide about this work. So what we did here is that we combined or co-trained a Lyapunov function and an ODE, or the vector field, that model the trajectories of the system. So it starts with the initial estimate of the Lyapunov function that gives us a conservative estimate of the region of attraction. And then we generate some samples from within this region of attraction and use these samples to estimate the ODE. Then we use we go to the next iteration of learning the Lyapunov function, generate samples, more samples from around the region of attraction, around the boundary of region of attraction, and use this to improve the ODE. And as you see, for example, in the section marked with number 1, you see that the green region is the true region of attraction for this van der Pol oscillator. And then as you see, the blue region is the estimated region of attraction at each stage. And we can actually multiply the value, the level value of the Lyapunov function corresponding to this region of attraction, and we obtain this bigger area, which is marked with which is shown with a pink area. So the pink area is where we generate samples and mark these samples. By samples, I mean the initial states, and roll out these trajectories from the initial states to see whether they enter the blue region or not. So if they enter the blue region, they're marked positive, meaning that they're stable, they belong to the region of attraction, the true region of attraction, or if they if they don't enter the blue region, then they're marked with negative labels, meaning that they're not stable. So then we actually use this to improve the Lyapunov function. As you see, when we go to the right, in stage 3 and 4, the region of attraction, the blue region, converges to the true region of attraction. So meaning that the Lyapunov function gives us a good estimate of the rho. And then during this process, so that only shows the progress for the region of attraction for the Lyapunov function and rho. But in the second section, this is the sampling process. So meaning that while we are improving the region of attraction and Lyapunov function, we generate samples, or we choose some initial states from within the region of attraction, but near the boundary of this rho, to generate some trajectories. And then we use these trajectories to learn the ODE. So as you see, because it is within these samples are chosen from within the region of attraction, they are already stable. So we're not worried about the stability, and they are also informative about their ODE within the region of attraction, which is what we care about, because we want the system to operate within the region of attraction. So this actually gives us some efficiency because we don't need to waste experimental budget for outside of the rho. And moreover, we can actually use the Lyapunov function, the estimate of the Lyapunov function, to regularize the learned vector field. And the way to do that is to basically learn to make sure that the ODE, or the learned dynamics, satisfy the negativity condition of the Lyapunov function. So this we usually do in the reverse direction. So for example, when we have the ODE, we try to learn a Lyapunov function that satisfies this negativity condition. But here we do it in the other way around. So because we fix the Lyapunov function at each stage, and then use that Lyapunov function to limit the hypothesis space for the ODE. And this means that we limit ourselves to the space of the functions whose lead derivative is negative along the trajectories of the system. When multiplied, I mean, the lead derivative of the Lyapunov function is negative when over the trajectories of this vector field. So this actually gives us more data or better data efficiency when training or when learning this ODE. So this work, the idea of this work is again to combine this algorithm, this iterative algorithm for learning the Lyapunov function, but now for learning the controller. So instead of learning the ODE, we try to learn the controller together with the Lyapunov function. So that's why it's called basically Lyapunov Redesign, and I will explain shortly why this or how this is connected to this classic idea from nonlinear control. So I will start with a very short introduction to the control methods in linear control, and then just a very brief introduction to some known methods in nonlinear control. So in linear control design, the controller has some standard methods which actually we can follow kind of mechanistically. So for example, if you represent the system as x dot equals ax, where a is the dynamics matrix, then there are all sort of standard methods like pole placement in state space, or state domain. We have frequency domain methods like Bode and Nyquist diagrams. We have H infinity. So all these methods actually are kind of a standard methods. There are also good heuristics and good also softwares and also visualization for example, how changing some coefficients of the PID controller change some properties of the step response. For example, changes the overshoot of the response, or the speed of conversion. So all these things have been derived over years, and we know all these things. So it's basically a kind of a solved problem in linear control. However, in nonlinear control, it's not like that. So just for example, in linear control, again, when you have access to the full state feedback, then you can design, and again, if the system is controller, you can design the controller, which in this case is a gain matrix shown by K. You can design this controller such that it basically shape the response of the system. So you have actually full control over the system. So in nonlinear control, it's not that easy. And so many methods are kind of ad hoc to a particular type of systems. We have gain scheduling, feedback linearization, backstepping, sliding mode, and Lyapunov Redesign as some starting methods in nonlinear control that I will just briefly present. So for example, in gain scheduling, the idea is to linearize the system at some working points. So for example, we know that system works at some operating points. And then if you linearize the system, we can actually use some gain or design some linear controller for that particular working point. And then this gain or this controller make sure that the system remains stable or meets the desired criteria for the closed loop system within that region. And then, of course, we need some detectors or some sensors to detect whether the system changes its working point or the operating point, and this changes the controller too. So this means that we design, let's say, a set of controllers for the different operating points, and based on what operating points the system is living now, it basically chooses that gain. So there are some problems here. For example, the transition from one operating point to the other might actually hurt the system if it's not smooth. Also, this does not actually make use of the nonlinearity of the system, because sometimes it's good to also have the nonlinearity of the system, which actually results in, for example, more energy efficient controller. For example, a controller that is aware of some nonlinear components can actually cancel that components and make a better use of the inherent nonlinearity of the system. So the other nonlinear control method called backstepping has this interesting and also I think kind of also more like intuitive idea that you can design the controller based on this recurrent algorithm. That, for example, you start with some subset of the system that you can control, and then, for example, you can consider this x dot equals f of x and g of x times z1 as that subset of the system, and then assume that that z1 is a control signal that controls this system. And then for the next system, shown in the second line, Z2 is designed such that Z1 satisfies the condition that it has to meet in the previous system. So then this means that Z1 acts as the controller for X, Z2 acts as the controller for Z1, Z3 acts as controller for Z2, and so on and so forth, until U, which is our actual controller, actual control signal, acts as a controller for ZK. So this means that we have, so U, which is our external control, has its immediate effect on ZK, and ZK has its effect on the previous state, and this goes all the way to the states of the system. So this also has to make sure that the system has this particular shape, but this is actually one method in nonlinear control systems. The other method is it's called sliding mode. So the idea of a sliding mode is to push the system towards some manifold or some subset of the status space, and then make sure that the trajectories of the system remains within this manifold, because this manifold has this, for example, nice property that every trajectory of the system confined to this manifold always goes to the desired equilibrium. So then the control problem becomes actually pushing the system towards this manifold. So again, this needs to satisfy some certain condition for the system, and also system must actually take this particular shape. Okay, so The next idea in classic nonlinear control is Lyapunov redesign. There's also feedback linearization. I didn't bring it because it's kind of more intuitive. So feedback linearization tries to cancel the nonlinear part of the system and then treat the rest of the system as the linear system. So this means that the controller must be somehow aware of the nonlinearity of the system, which sometimes is not the case. So nonlinear control, the Lyapunov redesign is a method to do nonlinear control. And the way it works is that let's assume that the system has some nominal part and some uncertain part. So the nominal part shown by this zero subscript is basically something that we have a controller for. So it could be, for example, some linear subsystem of this of the entire system that we know how to control. So we have a controller for. And also we have a Lyapunov function for this closed loop system. So these are two information that we need to know about this system. And also the uncertain part or kind of unknown part of the system shown by Fs star and Gs star are bounded. So they're bounded by this eta tilde. So they're both pushed into this eta, and then the norm is bounded by eta star, by eta tilde. So now the idea is how we can actually construct or extend the controller. So the nominal controller P0, how can we extend this controller with another controller or additional controller shown with PS star that we can, so that we can control the whole system. So by whole system, I mean the F0 plus Fs star and G0 plus Gs star. And then to do that, we can calculate the derivative of or the time derivative of the Lyapunov function, and then we see that this this unknown part, this eta part, appears in the right hand side, which is the bound of the upper bound of this of the time derivative of the Lyapunov function. So the interesting thing is that there is this Wx in this upper bound, and this depends on the Lyapunov function itself. So if we want to make sure that the Lyapunov function, the derivative of the Lyapunov function is negative, then this W or omega function needs to be a function of the Lyapunov function itself. So this means that the additional part or the additional controller uses the information of the Lyapunov function, of the existing Lyapunov function of the system. So meaning that the controller is informed by the Lyapunov function. So we use actually this concept in designing this neural Lyapunov redesign. So meaning that we use this iterative approach that achieves an estimate of the Lyapunov function of the system at each stage to design a controller for the next stage. And the controller is basically uses the knowledge already accumulated in the Lyapunov function and also the system itself to include more states inside the region of attraction that I will present shortly. So here is the algorithm. So the algorithm has two phases. The first phase, and these phases iterate. So the first phase and the second phase basically iterate until some criteria is met. So the first phase is estimating the region of attraction itself. So it basically uses the trajectories of the system to achieve an idea, or to achieve to estimate the Lyapunov function of the system, and then use this Lyapunov function to estimate the region of attraction. So the pi here is the controller, and n is the index of the iterations. So for example, at a stage n-1, what we have is the controller pi n-1, and also the region of attraction corresponding to the Lyapunov function estimated up to that stage, which is shown by r pi n-1. And then using this, we can actually collect the trajectories around the region of attraction with the method that I mentioned earlier. And then we can estimate or improve the estimation of the Lyapunov function. Then we can use this new Lyapunov function to estimate to obtain a new estimation for the policy. And the criterion that this policy has to satisfy when optimized this way is that some of the states which are currently negative, meaning that they are unstable around the region of attraction, has to be pulled towards the stability regions. So for example, if you look at the bottom left region, the figure that you see there, So the normal or the iterative approach for learning the Lyapunov function or region of abstraction is shown by these dashed lines, and as you see, there is this the green part, or the green region, is a true region of attraction, where there is an estimate or inner estimate of the region of attraction by this blue region, which is obtained by some Lyapunov function. And then we have this enhanced region shown by this pink area, from which we do sampling. And some of these samples are negative, some of them are positive, meaning that some of them goes back to the stability region, some of them, and the rest actually goes to the unstable regions. But then the idea is to actually try to change the controller. So as you see in this yellow arrows, so the yellow arrows is the effect of the changing the controller or learning the controller. So we use the current knowledge of the Lyapunov function to sample these points and then include them in or bring them back to the stability region of the current state of the Lyapunov function. So as you see, this is pretty similar to the neural Lyapunov redesign, meaning that the iterative approach to learn the Lyapunov function reaches at a state where we have a state of a good approximation of the region of attraction, and now it's time to enlarge the region of attraction by changing the controller. So there is multiple states or multiple iterations of the Lyapunov of learning the Lyapunov function, and then when it reaches a good state, then we fix the Lyapunov function and we do some iterations to learn the controller. And the controller, the criteria that it has to satisfy is including some of the unstable points in the region of attraction. And as you see in the right, so there are some pseudocodes here, but basically the loss function that we optimized for this problem. So on the top right, you see the loss function for learning the Lyapunov function, which is basically a classification loss function. And also you see the loss function that we optimize for learning the controller in the bottom right. So pi is the controller, and this is optimized with respect to controller. And the loss function basically is a function of the Lyapunov function of the previous state, and also the trajectories which are collected from around the region of attraction. So it tries to satisfy, so it tries to change the policy such that the closed loop system satisfy the negativity condition for the current state of the Lyapunov function. So that's how it actually connects to the neural Lyapunov redesign method. So there are, of course, some assumptions that need to be satisfied for this to work. And to make it more concrete, we can actually define this or maybe phrase this problem in a more mathematically rigorous way. So assume that what we want to achieve is some members, or at least one member of this pi star function, pi star set. So pi star set is a set of all the policies that maximize the volume of the region of attraction, where the volume is, for example, measured by some Lebesgue measure. And then basically, so if we define it that way, then we want to find the one sample or one example of these policies. So we can define a map from the policy itself to the region of attraction, and also to the volume of this region of attraction. So this is a map that, and the reason we can do that is that basically pi is part of the closed loop system, and if we fix the system, then the region of attraction is only a function of pi. So then the map from pi to the volume of the region of attraction is not easy to estimate. If it was, then it was easy for us because we could just backpropagate the information all the way to the pi and perturb the parameters of pi so that it increases the volume of the region of attraction. But then what we have to do is to use the Lyapunov function as a bridge. So Lyapunov function basically connects these two, because the policy affects the Lyapunov function, and the Lyapunov function itself gives us a way to estimate the region of attraction. So this is actually the challenge. This map is not computable, so we use the Lyapunov function to estimate this map. But the problem is that if this map is not is not smooth, or let's say if it's not continuous, then this is a problem for this algorithm. And the problem is that we want, so this is an iterative algorithm, and the information of the Lyapunov function and the policy, both this type of information, are distilled or are encoded in some neural network. So the neural network uses the current information to basically catch up with the next state of the algorithm, or to estimate the next, for example, region of attraction. So it doesn't start from scratch, it basically continues. And we want this process to be continuous and to be smooth, so that the neural network does not go to the local minima or does not forget what it has learned so far. So then this map has to be smooth. So there are some conditions that need to be satisfied for this map to be smooth and to change slowly. So there are two main conditions. One condition is called, these conditions basically come from the characterization of the region of attraction. So the region of attraction, the boundary of the region of attraction is characterized by the critical elements of the vector field. So for example, so some of these critical elements, for example, are the limit cycles, or it can be the equilibrium points of the system. So it is important, for example, in the case of equilibrium points, that these equilibrium points, the eigenvalues of the Jacobian of these equilibrium points has to have a non-zero real values. Because if it was zero, then basically it changes the nature of the equilibrium by a small change. So whether it's positive or negative actually changes the nature of the equilibrium. However, if it's non-zero, then a small change does not change the nature, because it's, for example, if it's negative, it remains negative. If it's positive, it remains positive. So then this is one condition that has to be satisfied. It's called hyperbolicity. There's another condition called transversality, which basically means that the stable and unstable manifolds of the system have to intersect in a regular way. And in a non-special way. So by non-special, I mean, for example, they must not somehow be tangent to each other. And for example, in the left-hand side of these two spheres, you see how two manifolds intersect in a transversal way, meaning that if there is a small change, and if there is a small change in this manifold, the nature of the intersection remains the same. The nature of the intersection does not change. But if they're tangents, then a small change may result in a big change in the qualitative change in the nature of intersection. So these two conditions are often satisfied in physical and practical systems. But unless if there is a system or a special system that does not satisfy or does not meet these conditions, then using this iterative algorithm has to be with care to actually make sure that it is not this non-continuity of the map from the policy to the region of attraction does not break basically the smooth accumulation of knowledge which is distilled within the neural network. So we can actually make these assumptions until more concrete, so I won't go into the details, but basically the intuition is what I already stated, but yeah, so feel free to also see the paper for proof of this theorem. So basically, the theorem says that if these conditions are satisfied, then basically a small change in the policy lead to a small change in the region of attraction. So here are some experimental results. Basically, so one challenge when designing experiments is that we want to have a controller for which we know the effect of changing the parameters in the region of attraction, and this is actually hard to compute for the same reason that I stated, because we don't actually know how to compute the region of attraction for a general system. So then we actually use some intuitions or kind of physical heuristics that we have. For example, consider this inverted pendulum system, and then let's assume that we put a saturation function on the controller. So this means that the control signal has to pass through the saturation function. So the saturation function has two parameters here. One is the slope of the saturation, and the other one is basically the angle that controls the saturation level. And then we know how this affects the region of attraction, because, for example, when the slope is higher, then it allows to push more energy from the controller to the system. So it enlarges the region of attraction. And the same for the threshold angles. So we know how the threshold angles, because for example, if the positive angle becomes more positive and the negative angles become more negative, then the threshold is less severe. So this means that more energy can be pushed to the system. So in the scenarios that you see, so each of these scenarios means that one of these parameters of the controller was fixed, and we let the system or the algorithm to learn the other parameter. So in scenario one, in the left figure, you see that the y-axis shows the fraction of some domain around the region of attraction, which is filled by the evolution of the algorithm. And as you see, the green plot is that fraction for that state of the Lyapunov function, and it increases. So meaning that when we have when we change the policy, so each jump corresponds to one change in the policy, and within one jump. So this means that, for example, from so each of these flat areas in the green plot shows that the policy is fixed, but there are multiple iterations to learn the Lyapunov function. So the Lyapunov function catches up with the true region of attraction, which is shown with this green area, and then this green plot, and then when it reaches at the stage that we know that the Lyapunov function cannot be improved any further, then there is one iteration, or let's say one step of policy improvement. So this policy improvement leads to an increase or the enlargement of the region of attraction. And as you see, the region of attraction increases over the iterations of this algorithm, so that it reaches a point it cannot increase any further, or we have some kind of physical limitations. So then on the right is controller parameters. As you see that, for example, the angles. So here the angles are the trainable parameters. So the angles are moving in the right direction, meaning that the positive angle becomes more positive, the negative angle becomes more negative. And the only learning signal for the controller is increasing the region of attraction. So meaning that the controller learns how to increase the region of attraction of the system. The goal, which is not easy to obtain if you don't have the Lyapunov function co-trained with the controller. And for another scenario, we basically fix another set of parameters, which here is basically just a slope of the saturation function. So we fix the angles, and then we let the slope of the controller to be learned, and we see that the slope is going in the right direction. It actually increases over the iterations of the system. And as you see, the region of attraction, the true region of attraction of the system, which is obtained by improving the controller, also increases, while the Lyapunov function the trainable Lyapunov function manages to catch that increase. So here is basically the evolution of the algorithm, or the results of the algorithm, and from left to right, each row corresponds to a fixed controller. So the controller does not change. And then for a fixed controller, as you see, the true region of attraction is shown with a green region. And then from left to right, the Lyapunov function gets better. The Lyapunov function is being trained, and it becomes better up to the point that it achieves a good estimate of the region of attraction. As you see, this estimate is shown with a model raw, or that blue area. And then when it reaches that point, when the Lyapunov function cannot be improved anymore, for example, it could be due to several reasons. For example, the network that models the Lyapunov function is not expressive enough. For any reason, it cannot be improved anymore. Then it's a time to improve the region, to improve the policy. So then we fix the Lyapunov function, and then the next row, there is one iteration, or one step of improving the policy. So policy look at the samples from around the region of attraction, and then pull the samples, or gets updated in a way that these samples become part of the region of attraction. And the way to do that is to actually satisfy that negativity condition given the current state of the Lyapunov function. So as you see in the second row, the green region, which is a true region of attraction, gets bigger, meaning that we have a larger region of attraction. And then from left to right, the Lyapunov function improves. So the Lyapunov function does not start from scratch. It basically starts from the previous knowledge that has been accumulated, and then it tries to smoothly gets adjusted to the new region of attraction. And then it reaches a point that it cannot improve any further. And then there is a next round of policy improvement. So from top to bottom, the policy gets updated, it improves, and then in the bottom right, it's basically the final state of the algorithm. So the policy gives the biggest or the largest region of attraction achievable within the physical constraint of the system, and the region of attraction is well captured by the Lyapunov function. So this is actually the final state, and also the basically what we want to achieve at the end. So there are more theoretical considerations, for example, so these theoretical considerations would be useful in practice too. For example, when you want to use this algorithm for a certain type of systems. So one thing to consider is the rate of growing the Lyapunov function. So basically the occasion that this becomes important is when we want to do sampling, or we want to collect samples for choosing or detecting the negative or positive samples around the region of attraction. And then so what we did, for example, in these figures in the left, you see that there are two regions. One is the blue region, the other one is the pink region. And then the blue region is where the inner estimate of the region of attraction. The pink region is where we do the sampling. And the difference between these two is obtained by multiplying the level value of the Lyapunov function with some positive number, or with some number which is larger than 1. So how to choose this number? So this number, for example, if there is a very high slope for the Lyapunov function around the boundary, then this number, even like a small number, or a number which is just slightly more than 1, leads to a big increase in the sampling region, and this means that many of these samples would be negative. So this is also an interesting connection between the machine learning perspective and this controller design perspective, because so in machine learning, when we want to solve a classification problem, we prefer that the data set is balanced, meaning that we have the same number of negative samples as the number of positive samples. And then this is controlled by the slope of the Lyapunov function near the region of attraction. And then we can actually control it here in the loss function, because this slope is basically a function of the Lyapunov function, which is the norm of the gradient of the Lyapunov function with respect to input. So instead of taking the derivative with respect to the parameters, which is used for learning, now we take the derivative with respect to the input of the Lyapunov function. So this again is a function of the parameters of the Lyapunov function, and we can easily calculate it with the automatic differentiation framework. So this can actually be part of or can be one term in the loss function that we learn and that we use for learning the Lyapunov function, and then it controls the slope of the Lyapunov function. So there are more theoretical considerations, for example, which has the values when we actually see this as a learning problem. So in machine learning, we always want the gradients to be large, but not too large. So it must be large so that it makes the algorithm or the network trainable. But we want it to be somehow limited, because if it's too large, then it pushes or basically changes the state of the neural network to some state which is actually not desirable for us. So it may also lead to something called catastrophic forgetting. So it just forgets what has been learned so far. So this theoretical consideration basically says that how we can actually calculate the gradient in a way that somehow limits the possibility or limit the chance for this explosion gradient or this vanishing gradient conditions. And the reason it's important is that this is so this algorithm is not, let's say, a normal machine learning algorithm where we have a single loss function and then we can look at, let's say, different conditions of this. For example, we can maybe limit or maybe yeah, for example, we can make sure that the neural network does not saturate, or this kind of normal things that we do when training a neural network. So here the problem is that we are training two components together. So one component is a controller, and the other one is the Lyapunov function. So the training, also the gradients that are used to train to learn the controller passes, these gradients pass through the Lyapunov function. So this means that the one component affects training of the other component, so by affecting its gradient. And we can actually check how it affects that by taking gradient with respect to the parameters of the controller, and then expand this function, the loss function L of pi, with respect to the gradient, to the parameters of the controller. And then we see that there are different components to this expansion. So one component is the gradient of this loss function with respect to the final state of the trajectory. So as I said earlier, we use the trajectories of the system to train the controller and also the Lyapunov function. But here we're focused on learning the controller. So if the trajectory is rolled out for too long, and if the trajectory is stable, then it goes near the equilibrium of the system. And we know that the Lyapunov function and its derivative vanish near the equilibrium, or at the equilibrium of the system. And if it's continuous, then it means that it has a very small value near the equilibrium. And then this means that it somehow reduces the magnitude of the gradient when taken with respect to the state near the equilibrium. So this suggests that we should not roll out the trajectories for too long. Also, if it's unstable, so this is for the stable initial states, but if it's unstable, then we also have to be careful, because so rolling out the trajectory for too long, we go to some dangerous areas of the state space. So the other term in this loss function, the second term, is basically how the current state of the trajectory affects the future state of the trajectory, which is controlled by the dynamics of the system. So this is not in our hands, but we can actually detect that, for example, if the dynamics is very slow, then this means that the change in this, let's say in the current state, which is caused by the controller, does not lead to a big change in the future states. So this is also important to know, because, for example, when we know that this is slow, then we have to compensate it with the other components. And the last component in this, or the last term in this gradient of the loss function, is how the dynamics is affected by the controller, and how the controller is affected by its own parameters. So the way that the dynamics is affected by controller, again, is not in our hands, because this is something depends on the controller parameters, or the controller physics of the system, of the closed-loop system. But for example, the way that the controller is affected by its parameters is something we can improve. So for example, if the controller is kind of flat with respect to its parameter, then this is not good, because then this means that changing the parameters of the controller does not change anything in the closed-loop system. So this is actually the conclusion of this method, but I want to also make some general remarks about this work, and also the previous works, and also how I see these two works together. Basically the idea of this work, and also that earlier work, which was training Lyapunov function and ODE together, was something that I called gamification of the control problems. And the idea, or the kind of explanation for this gamification term, is considering the kind of control problem as a game. So instead of seeing it as an optimization problem, for example, in optimal control, that we have a loss function and then we try to optimize this loss function, the question is, can we see it as a game between different components? And so there are some methods, especially some recent advances in machine learning, that, for example, principal component analysis was shown to be can be solved as a game between different components, and this could actually be very scalable to high-dimensional problems. So can we do that in control problems too? So what I showed today, and also the earlier work, learning the ODE and Lyapunov function, showed that we can actually see this as a two-player game, where one player is the Lyapunov function, the other player is the is basically the ODE learner or the controller. But we can maybe think about more games, or maybe games with more players. So normally in control theory, we consider the problem. So it starts from the system, then we do system identification. If we don't have the system, then we try to design the controller using that identified system. If we want to also estimate the region of attraction of the system, we try to also estimate the Lyapunov function from the closed-loop system, and then use this Lyapunov function to estimate the region of attraction to see how to assess the stability of the system. But then the gamification basically says that, can we estimate everything together? Can we estimate the controller and Lyapunov function together? For example, in this work, can we estimate the system identifier and Lyapunov function together? In the earlier work, or maybe can we just estimate everything together? So the natural extension is system identification, Lyapunov function, and controller, train them together. And then this co-training has actually benefit for every component, because, for example, the Lyapunov function can benefit the controller, or it can also benefit the system identifier. And system identifier can also benefit the Lyapunov function by providing some kind of inductive bias to the network, or the function estimator that is used to capture the Lyapunov function. So that's actually the final slide, and that actually concludes my presentation. So thank you for your attention.
All right, thank you very much. Thank you. Any questions or comments?
Yeah, just curiosity. You mentioned, and in dynamical systems, we talk about attractors.
Mm-hmm.
So is there any in your talk or about the dimension of the attractor?
You mean for this particular method, or in general? Maybe if you explain more a little.
I have some hope that if we know the dimension of the attractor, we can reduce the dimension of the problem.
Yeah,
and
so that's
you mentioned multiplayers, and the case of dimensionality is still here.
Mm-hmm. Yeah, so I think probably one thing that machine learning can provide to control is actually to learn these low dimensional manifolds in which the system operates. Because, so for example, we know that the neural network is a way to somehow model this or somehow capture this low dimensional manifolds within a big or a large dimensional or high dimensional embedding space. So maybe this is kind of a one way to impose this inductive bias. But in general, yes, so in higher dimensions, we're usually facing with this problem.
Another one is there is something called reservoir programming or doing machine learning, like modeling the reservoir.
Mm-hmm. Yeah.
And the question is, you talk about controller, and in the dam of water level problem, there is a situation where we want to control the level of the water. So is there some connection that I can draw between your beautiful analysis of the controller to the reservoir dam problem?
So you mean for a particular task, or maybe I think I didn't get the question clearly. So you mean using this method to solve that problem, or?
Using your method to learn more about the dam water problem. You know about the Hurst constant.
Yeah.
Okay, so I like to draw similarities and analogies.
Mm-hmm.
So sometimes I don't follow the details of, the fine details of the talk, which is wonderful and very elaborated. But you know, after the talk, what am I taking away? So that's what drives me. Maybe it's not related to your talk, but
yeah. But yeah,
I'm open to be criticized, you know, in a friendly way.
We can't hear you. I think we are losing you.
Oh, you can't hear me? Sorry.
Yes, so your voice is on and off here.
I say I'm open to be criticized by trying to find similarities or usefulness of certain model to another model, to another problem.
Yeah.
So that's why I'm asking these kind of weird questions.
No, I think it's interesting. I think there are a lot of similarities. So, for example, I mean, it's always good to find, for example, some abstraction and then generalize that abstraction in different problems. So I'm not fully familiar with that context to be able to make a precise comment. But yeah, I'm happy to also chat about it as well.
Okay, thank you. It's a great talk.
Thank you very much.
Any other questions or comments? I have a question about for example, if you come back to like backstepping, for example, and I mean, did you apply this to the context of backstepping, for example, where you construct the Lyapunov function for the first level, and then you propagate and then see what happens? I mean, because the advantage of backstepping or feed-forward structures is that you have some analytic results. So did you try to apply it to cases whether it's upper triangular or lower triangular, and then to get like analytic results for your method, or no?
No, we didn't apply it to backstepping, but I mean, at conceptual level, it's very similar to this one too, because this actually have this kind of a recurrent nature, that you start with something that you know it's basically stabilized, and then you try to extend the kind of controller to something else, to basically a shell around this system.
Yeah.
But it's kind of different because here you have to, for example, first design a control signal and then solve another system that, I mean, the output or basically the state of that system is the control signal for the other one. But in nature, I think it's very similar to also, I mean, the way that also showed the Lyapunov redesign, that we have, let's say, some subset of the system, and then we try to extend the controller. But actually, we just use it as a kind of a conceptual, intuitive level. We didn't, specialize the method to this.
Yeah. Okay. All right. Okay. Thank you. Any other questions or comments?
Something about the language. It's on some slide you had learning signal, and I thought you meant learning the signal, but maybe there is a signal that is induced by the process of learning. So I'm a bit confused about that.
Yeah, it's a terminology which kind of a standard in machine learning. So learning signal is basically the signal, or let's say the information, which is used to perturb the parameters of some sort of a neural network to basically improve it, right? So for example, learning signal is the gradient of some loss function with respect to the parameters. So that's what we call learning signal. So it's not learning a signal that, for example, we have in, let's say, signal processing.
So it's a given signal that we are probing the system with.
So learning signal is basically defined within the context of, let's say, learning or machine learning problem, but basically it means that the information that we can provide by backpropagation of some error towards the parameters. So, and signal basically more is like an information, which is a gradient of some scalar to the parameters.
Okay, fantastic. Thank you.
Sure, thanks.
All right. Any other questions or comments? All right. So it seems that there are no further things. Okay. Thank you, Arash, very much for this talk.
Thank you very much for having me.
Thank you. Bye-bye. Thanks. Have a good day. Thanks. Bye-bye, everyone.
Bye.